sequences today, geometric and arithmetic sequences, and specifically we're going to be connecting geometric sequences to exponential functions, okay? Sounds way harder than what it is, I promise. Okay, let's go to our next slide here. Here are our TEKs, and our objective today, we will identify and create geometric sequences relating each sequence to exponential functions. Okay. All right, our vocabulary. First one, geometric sequence. A sequence in which each term after the first is found by multiplying the previous term by a constant r called the common ratio. Let me give you a for example. Our example will be, let's say that you have like a 1, okay? Let's see. You have a 1, a 5, 25, right? And so when we're looking at this, the relationship here is that here I'm multiplying 1 times 5, and I get 5, right? 1 times 5 is 5. 5 times 5 is 25. So what do you think the next term would be? 125. Good. Okay, so this is essentially a geometric sequence when you multiply by the same thing. Now, what would your common ratio be? Okay, our common ratio is whatever you're multiplying it by, right? And so in this case, it is actually 5, our common ratio. And I'll show you in the next one more how to calculate that another way. A counter example might be something like this, where I have 1, 6, 11, 16, 21. Here, I'm doing something with 5, but I am adding 5 each time, right? This is not a geometric sequence, okay? So that is our counter example. Let's go ahead and let's look at our next. Any questions that you have along the way, please feel free to come see me and we will clarify that for you, okay? Common ratio, that is the number that we were multiplying it by whenever we're talking about geometric sequences. So the ratio of successive terms of geometric sequence. So for example, let's say that we had the 1, the 5, the 25, and the 125, right? What you do to calculate the common ratio, and remember again, we said, oh yeah, we know we're multiplying it by 5 every time. But one way that you could do this is you take essentially the second term and you divide it by the first term. The reason we do this is because it's easy enough to see here in this baby example, but you might get a sequence that might be a little tougher to see. And so if you know the basic formula, you just take your second term. So let's take 25 and we divide it by 5. Or you can take 5. I'll probably do that one just so, oh no. Okay, I'm better now. Let's take 5, our second term, and let's go ahead and divide it by the term there. So, I was going to do 25 divided by 5, which ends up being the same thing. The idea is you take any term, divide it by the term before it, and you will get your common ratio. Okay, our counter example might be something like 1, 5, 50, and 100. Okay? And in this case, we would be multiplying times 5. Okay? This one, we're going to be multiplying times 10. And this one, we're multiplying times 2. So notice how each time you're multiplying, but you're multiplying by something different. There is definitely not a common ratio in this particular sequence. This sequence would not be geometric, and there's not a common ratio for this one. Okay, let's go ahead and move on. Example 1. So when we look at this one, determine whether the sequence is arithmetic, geometric, or neither, okay? An arithmetic sequence is one where you add the same thing every single time, okay? Um, let's take a look. And geometric is when we multiply by the same thing. And neither is neither. So let's look at the relationship here. I'm sure a lot of you are already seeing it, right? It looks like every single time we're increasing by 8. Very nice. 0 plus 8 is 8. 8 plus 8, 16. 16 plus 8, 24, and so on. Every single time we're adding the 8, okay? That makes this an arithmetic sequence, okay? The fact that we're adding 8 makes this an arithmetic sequence. So I'm going to go ahead and write that out. Yay. Easy. Good. Let's go ahead and let's look at the next one. Oh, there we go. Determine whether the sequence is arithmetic, geometric, or neither. Neither. When I look at this, let's try the first one. Let's see. If I am going this way, I am subtracting. I can always take, let's see, if I took 64 and I subtract 48, then I end up with minus, I'm getting 16, right? So I could subtract 16. Now let's look at this again. If I subtract 16 from 48, let's see. That's no good, right? So this is not arithmetic. Okay, let's try again. Let's see about that whole common difference thing with the geometric sequence. So we're looking for something that we would multiply. I don't know about you. I can't exactly see it right off the bat. So I'm going to use that formula, right? That common ratio where you take the second term and you divide it by the first term. So 48, and this is to solve for our common ratio, divided by 64, okay? When you put this in your calculator, you end up with, if you use Desmos or if you have a graphing calculator, you end up with 3/4, okay? So let's test it out. The idea is if I multiply 64 times 3/4, I should end up with 48, right? So 4 goes into 64. Oh, my calibration's off a little. Let's see. That's 1. And then that's 24. We're looking at 6. Okay. Times 3, which is equal to 48. Yay. Okay. And let's see if we did it again. We had 48 times 3/4. Okay. So 4 goes into 48. 12 times 3 is 36. Beautiful. Okay. So it's looking like it works. I mean, we can test it because, that last one could change everything, right? Let's say that we have, let's start off with 36 and we want to multiply that times 3/4. 4 goes into 36 9 times. 9 times 3 is 27. So yay, this works. Every single time we can multiply by 3/4. Therefore, this is geometric. Okay. Do want to throw this out to you, see how it goes. We were talking about exponential functions last time, right? So is this decay or is it growth? Are the numbers going up or are they going down? Okay. If you said decay, good for you. Okay. This is absolutely decay. And remember that if we were writing the equation, it would be something like y equals a times 1 minus r to the power of t. Yes. And so, or x, I forget, one of the two. But what would our rate be? I mean, this common ratio, we know we have a common ratio of 3/4, otherwise known as 0.75. Okay. And so is that R or is that 1 minus R? So here's the thing is that when we're looking at this, we're multiplying it by 3/4, right? The common ratio is the way that it would look like is this. Okay. And our initial value in this particular case might be 64. Okay. Therefore, what if my common ratio is 70.75? What is my rate of decay? Okay. If you said 25%, you are genius. Okay. Because these two are equal. Yes. 1 minus R is equal to 0.75. Let's go ahead and add R, 1. These are additive inverses. And we have R plus 0.75. Now let's subtract the 0.75. Additive inverses. And R will equal 1 minus 75 cents is 0.25. And 0.25 is the same as 25%. So I think that's an interesting thing to put together, right? Because we know we have a common ratio. We're multiplying every single time by 0.75. But we need to keep in mind that if they're telling us that the rate of decay is 0.25, then they're basically saying the same thing. Common ratio means that we have a rate of decay of, we're going to make that work, of 25%. So every single time, if we have 65 bananas, I don't know why I'm thinking bananas, but 64 bananas, if we have a 25% rate of decay, then the next time I only have 48, and the next time I only have 36, and the next time I have only 27, which sounds like my house. Okay. All right. Now, let's go to the next problem. Again, if you have any questions on this, just ask me and I will be more than happy to help. Let's see. Let's go to the next page. Come on. All right. So, yay. The common ratio is 3/4, so the sequence is geometric. Okay. Lovely. Let's move on. There we go. Find the next 3 terms in this geometric sequence. Okay. So, step 1 is find your common ratio. Okay. Identify the common ratio. Step 2, multiply by the common ratio. So here we go, common ratio. Take the second term and divide it by the first. So here we go. Second, -8. And the next one, 1. Oh, look, that's kind of weird, right? It's positive, negative, positive, negative. Okay, let's see if it works. So -8 divided by 1 is -8. So our theory is that we have a common ratio of -8. Let's see if it works. 1 times -8, -8. Great. -8 times -8, positive 64. Yes. And if you need to, go back to Nacho Dude. Remember that guy? Okay. Negative times a negative is a positive. We're going to multiply this again by -8. And according to my calculations, it does work. So every time we're multiplying by -8, this is definitely geometric. Yay. But that's not really what they were asking for, right? They said, what are the next 3 terms? Okay, well, great. Let me do it 3 more times. I've got negative 512 times -8. That will give me I'm so glad I did this ahead of time. 4,096. Positive, right? Okay, we're going to do it again. So this is going to be, yep, that's that. So then we have 4,096 times -8. We know it's going to be a negative, and it's negative 32,768. Okay. Yeah, and just off the top of my head here, negative 32,768 times -8 is 262,144. Ladies and gentlemen, these are our next 3 terms. And that negative is included as well. Okay. Last one for today. Yes. Let's go ahead. Let me clear this out. Example 2b, exponential growth. Find the next 3 terms in this geometric sequence. Okay, these look like smaller numbers. Hopefully it's easier. Let's go ahead. Number 1, find the common ratio. Number 2, multiply. Got it. Here we go. Which one goes on top, 20 or 40? 20. Good job. Divided by 40, which is 2 over 4, which is the same as 1 over 2. Okay, so our common ratio is 1/2. Let's see if this works. What is half of 40? 20. Awesome. So we are multiplying by 1/2. I know that looks like a plus. Okay, I'm going to go ahead and try and make it look like 1/2. And then again, what's half of 20? 10. Half of 10? 5. Awesome. Okay, so the next 3 terms are going to be, and you could do it in fractions. I'm going to do it in decimals this time just because I feel like being difficult. So here we go. 5 times, I can't let that go. Here we go. 5 times 1/2. Half of 5 is 2.5. It's like half of $5 is $2.50, right? Okay, so then that's 1. And I got 2.5. What's half of $2.50? $1.25. And then finally, what's half of, well, it stops working with money here, I guess. What's half of 125? According to my calculator, we're looking at 0.625 right there. And so those are our next 3 terms in our geometric sequence. So that's it. A lot of complicated words, but pretty easy concept. If you would, go ahead and I'm going to take all the way, let's see, right here. In the comment, if you would send me a private comment kind of thing, just kind of tell me where you're at, 1, 2, 3, or 4, or 5. Okay. And I hope you have a fantastic day. Take care. Bye-bye.